combustion simulation package, Arrhenius.jl. So this I would like to start from this famous diagram from Professor Lu and Professor Lau. The complexity of detailed kinetic models, especially for large hydrocarbon field. And this diagram is usually referred to imply the challenges in simulating detailed combustion chemistry. And actually here, we highlight another challenge is to develop a complex kinetic model, as we have more rate parameters to determine. And this complexity has imposed challenges for both experimentalists and computationalists. From an experimental standpoint of view, that we need large data sets to measure more important species and cover a more wider range of conditions. And from a computational point of view, we have to optimize more parameters, and also each time we evaluate the model, we take more time. So essentially, the challenge is how to do high-dimensional nonlinear optimization. And so before jumping to differential programming, let's first review how we do optimization. So in the past, so normally we use the evolution algorithm to optimize combustion model, such as genetic algorithm and particle span. So those are approaches are very easy to implement, and we can very easy to parallelize the optimization. But the major change for evolution algorithm is that the computational cost scales with the number of parameters and also the number of data samples, so that it's not suitable for complex kinetic model and the big data set. So the motivation of developing Arrhenius package is to optimize complex kinetic models with hundreds, even thousands of parameters, and utilizing big data sets from high throughput experiments. So the way we do it is to generalize the techniques used for training deep neural networks to combustion model, which is called differential programming. So it's not a specific technique, but instead a class of optimization techniques used for training deep neural network. So it has two parts, which can illustrate from the neural networks. So in the left side is showing the forward evaluation of the neural network, that we compute the neural network from the input to the output. And in the right side is the backward propagation, that we evaluate the gradient of the output to the neural network weights by compute the neural network in the backward direction. And by doing back propagation, we can efficiently compute the gradient of the simulation results to the model parameters. And the second step is we use this gradient information together with the stochastic gradient distance to optimize the complex neural networks. And this approach has shown super successful in the deep learning community. So here we try to generalize it to the combustion kinetic model. So with that, before jumping the details, let's see an example for optimizing more than 300 kinetic parameters using differential programming. It's working with the propane pyrolysis data from shock tube, and so it involves more than 100 reactions. So that each reaction has 3 parameters to optimize. So it results more than 300 parameters to optimize. And we did this optimization with less than 100 lines of code and takes less than 4 hours on a common personal computer even without the high performance computer. And this is actually pretty much the highest dimension ever achieved for combustion optimization without the parameter selection. So the package behind the task is this Arrhenius.jl. You can essentially view this package as a common key with a differentiable capability. And also it's open source so that everyone can access the source code and contribute to it. And so by default, it also you can also easily make the support GPU and also augment neural networks to represent part of the physics and optimize the neural network. And so to better illustrate how the differential programming works for combustion, we can use this one-dimensional flame example. We have different source terms, and at the low level, this differential programming can compute the gradient of these each source terms with respect to the model parameters. And with this elemental computational block, we can also differentiate the entire combustion simulation code. So which usually compute the gradient of the species profile, ignition, flame speed. So with respect to the model parameters. So the reason is that those variables are the quantities are the one that we can measure directly from experiments so that we can use it for the training. And so in addition to the model parameters, we can also compute the gradient with respect to the boundary and initial conditions, and also the augmented neural network submodels. And we will show this those capabilities can enable us to do some new computational tasks. And so today I will mainly talk about 3 example applications of the package, and also another 2 ongoing applications. So the first one is to do maximum reduction. So the motivation is that conventional maximum reduction would keep the rate constant unchanged while removing pathways. And here we want to go do further reduction. And so using a 2-stage process, we first overly reduce the maximum, and then we retrain the maximum to balance the size and accuracy using ignition data. And the training is essentially using the differential programming with stochastic gradient descent. And then finally, we validate the retrained model with ignition delay and also flame speed to covering a wide range of conditions. So this approach has shown advantages than other evolution algorithms with better fitness and also better generalization. And those are 2 example cases with GMAC for natural gas, and another one is Manhattan for diesel engine simulations. And so overall, the steep reduction maximum works well for both ignition and flame speed, even we don't have flame speed in the training data set at all. And so the key to the success reduction is we can optimize hundreds of parameters involved in the overly reduced maximum. And since the optimization is so efficient and robust, we can actually further reduce the maximum if we have a more specific application or targets. And so in terms of the computational cost, we do this optimization within about hours on a normal personal computer. So for comparison, like evolution algorithm will have to run a high performance cluster. So the second application is to do uncertainty quantification using active substrate method. So the motivation is that uncertainty quantification is usually very challenging for complex model, since because we have too many uncertain parameters. And there is a promising approach called active subspace. So it seeks the low-dimensional subspace by doing principal component analysis in the gradient space, so that we can do the uncertainty quantification within this low-dimensional subspace, which is much easier. So the major challenge with active subspace method is how to efficiently compute the gradients. And here again, we do the differential programming applied to the GMAC and also the detailed inheritance maximum. And we especially the inheritance maximum has around 5,000 reactions, which is probably the highest dimension ever achieved for combustion uncertainty quantification. And we also observe the one-dimensional subspace for the inheritance. So which means we can actually leverage this one-dimensional subspace for low-cost uncertainty quantification for even larger hydrocarbon. So in terms of the computational cost, this differential programming reduce the computational time from 1 hour to 1 minute for the GMAC. So another example application is model discovery. So the idea is that so normally we develop combustion kinetic models based on expert technology. So it's a manually derived model or approach like IMG based on a proposed candidates library. And here we don't have to produce, so we don't have to provide any prior information. We simply use a neural network to represent the combustion chemistry and augment the neural network into the governing equation and optimize it against with experimental data. And so here we apply it to the high-chem model to learn the pyrolysis steps using an interpretable neural network model called chemical reaction neural network. And we so with the capability of optimizing the hundreds of parameters in the neural network, we get a neural network that can accurately predict the ignition delay time comparing to the training data. So in addition, the neural network that learned is also interpretable, that we can translate the neural network into a chemical format reaction maximum. And you can learn more about this neural network architecture in our another talk in the fire research session. So we also have some ongoing applications, including data estimation and inverse modeling. For the data estimation, the idea is to combine kinetic models and high fidelity experimental measurements to get a better understanding to the species profile. And here we simulate the propane pyrolysis data from shock tube. And so by optimizing more than 300 parameters, that we can inference the species profile shown in the solid lines, which has much better agreements with the experimental data comparing to the baseline model. So for the inverse modeling, we applied to industrial combustor using a perfect stirred reactor model. So the task is that we have the measurements at the downstream, and while we don't know the conditions in the upstream. And here we approximated the upstream conditions using a neural network model since it's unsteady. And we use differential program to train this neural network. And the approximated upstream conditions shows very good agreement to the ground truth value. And so all the above example applications are also accessible on GitHub. And also we also have a document to facilitate developers. So in a summary that we have shown this package can enable user access to differential programming for optimizing complex combustion kinetic model. And it shows benefits in many different computational tasks. And this actually, this is the beginning of the exploration. And so there's a lot of other potentials on the way. And here are some preliminary thoughts that we think that is in the agenda of the development. So the one dimension is to enhance the functionality and the scalability to do more complex reacting flow simulation. Another dimension is to enable multi-phase and multi-physics combustion simulations. And so one of the very exciting feature of Julia programming language is that it has very good readability and transparency in a sense that you don't need a very good programming skills in like C++ or Fortran, but still you can make your own physics model at a very short time period. And to better illustrate the potentials of this package, we also have wrote several short conference paper about the mentioned applications, and you can also check out the code on GitHub. Yeah, finally, I would like to thank our developers all over the